welcome to this lecture about neural networks. Let's start with a motivation about why you may need complex nonlinear models. Suppose that you have a dataset like this, where the two classes are not linearly separable, and you want to apply a logistic regression model to this dataset. One thing you can do is to create more features based on your two original features. So you will end up with a hypothesis function like this one, where g here is the sigmoid function. And if you include enough features or enough polynomial terms like those, then maybe you will end up with a hypothesis function that separates the two classes sufficiently well. Here we had just two features originally, and then we created more features based on those two. But in general, we have datasets which include much more features. So for example, let's say 100 features. And based on those 100 original features, let's say that you create second-order polynomial features because you want a nonlinear decision boundary in your original feature space. So you will end up with a lot of features. So you'll have, for example, x1 squared, x1 times x2, x1 times x3, and so on. And then x2 squared, x1 times x2, x3 squared, x100 squared, etc. So the number of new features that you will get is in the order of d squared, where d in this case is equal to 100. And that's only for a second-order polynomial. Imagine that you want a much more complex decision boundary. So you need to create polynomial features of degree, let's say 3, 5, and so on. So you will end up with a huge number of features. And the problem with this is that it becomes very computationally expensive to train any model, but you are also more prone to overfitting if you are not careful about, for example, regularization. And you may, for example, decide to include just a subset of those created features, but this may be not enough to fit a very complex data set or to get sufficiently complex decision boundary. So this doesn't seem to be a good way to learn complex nonlinear hypothesis functions. And in many real-world problems, the original number of features, d, is very large. For example, your dataset consists of images, and then you get an image and you want to recognize what this image contains. So in this case here, it's a cat. But your camera or computer sees this, just a bunch of numbers. And each number represents, for example, the pixel intensity value. So here, each pixel can be seen as a feature which describes the image. And based on these pixel values, you want a machine learning model that tells you that this is a picture of a cat, or this part here is the nose of a cat, for example. Suppose that you have a training data set of images, where each image is labeled as a cat or a dog. And you want to train a classifier that tells you if a given new image is a cat or a dog. If each data is, for example, a 50 by 50 image, so you have a total of 50 by 50 or 2500 pixels or 2500 features, because we considered each pixel as a feature. So an image will be represented by a data point in this 2500 dimensional space. And here I'm just simplifying and illustrating with 2 pixels just for visualization purposes. But each image in your training dataset will be a high dimensional data point. And you want to fit a machine learning model to this high dimensional data. And here we have 2500 features only if we consider those as grayscale images. So we don't take the colors into account. But if you want to do that, then each pixel will have 3 values, the intensity of red, green, and blue. So you will end up with 7500 features. And now you want to fit a nonlinear model to this data. So you may think of creating additional polynomial features based on those original features that you have. And if you just create quadratic features, then you will easily end up with around 3 million features. And maybe that's still not enough to have a complex decision boundary that correctly separates the two classes, cats and dogs. So maybe you want to create more features based on the original ones in order to fit, for example, logistic regression model. But again, you will easily end up with a huge number of features, which is not good. So using a simple method, for example, logistic regression, together with adding polynomial features, is not a good way to learn complex nonlinear hypothesis functions, especially when the original number of features d is very large, because then you will end up with way too many features. And it turns out that artificial neural networks are a much better way to learn complex nonlinear hypothesis functions, even when d is very large. And neural networks can be used for both classification and regression also, and some more stuff like, for example, feature learning or dimensionality reduction, or for example, when you want to generate new data using what we call generative models. So for example, you have a data set of cats and then you want to generate a completely new cat, which does not exist in your original data set. And they can also be used for more stuff. But this lecture is an introduction to neural networks. So we will start with simple things, and then later in future lectures, we will see some more advanced things that you can do with neural networks. Okay, let's now try to define what a single neuron is. And here we are talking about an artificial neuron, and sometimes it is referred to as a unit. To do so, let's start from a simple logistic regression model. So here, for example, we have this vector of parameters, and our input data is described by 3 features, x1, x2, and x3. And as usual, this is an additional feature, x0, which is equal to 1. And we do this so that we can compute theta transpose x, which is used here in the hypothesis function. So this is the hypothesis function we used for logistic regression. So it computes theta transpose x, and then it applies the logistic function or the sigmoid function on this. So we can write our hypothesis function in this way. First, we compute the dot product of theta and x, and then we apply the sigmoid function on this. And sometimes we call this an activation function. We will see this more about this later. Now let me take the input x shown here and the parameters theta shown here, and then represent the dot product of x and theta in this way. So this is theta transpose x, theta 0 times x0, which is 1, plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. And then I apply an activation function g on this dot product. And in this example, our activation function g is just the sigmoid function. And what I am showing here is called a neuron or unit. The value that it gives us is the activation function applied on the dot product of this and this. And in this example, this will be our predicted output, the prediction of the logistic regression model. So a logistic regression model can be represented in this way if the activation function that we are using here is the sigmoid function. And in this case, we have an input layer here, and we have an output layer here, which contains just one neuron, and the arrows between the two layers are our parameters. And you can also call them weights. Usually in the context of neural networks, they are called weights. And so all this is the vector of parameters, theta. And the neuron applies an activation function g on theta transpose x. So we first compute the dot product of theta and x, and then we apply an activation function on this. And this additional feature x0 equals to 1 that we need to add is called the bias unit. And again, if the activation function g happens to be the sigmoid function, then this is just the logistic regression model that you know from previous lectures. So this is just a linear model because we have an input layer and we have an output layer, but there are no neurons in between. So if you use this for classification, then it will only be able to learn linear decision boundaries. Now let's see how to define a neural network model. In this example, we have 0 hidden layers. So here we have an input layer, and this is the output layer, but there are no neurons in between. So there are 0 hidden layers between the input and output. So this will be a linear model. And if you use here the sigmoid activation function, then this will be the logistic regression model that we used previously for classification. And here we have a neural network with 1 hidden layer, which contains 3 neurons or 3 units. And an architecture like this with at least 1 hidden layer is able to produce nonlinear models, like for classification or for regression. But the condition for this should be that the activation functions that we use at those neurons must be nonlinear functions, and they should be differentiable functions. So their derivative exists at any point. Okay? But if you use a linear activation function in all neurons, then such a model will not be able to produce a nonlinear decision boundary like this one. It will be just a linear model, no matter how many hidden layers you have. So this is important. Your activation functions should be nonlinear functions, and they should be differentiable functions, as this is important later when we train the neural network with, for example, gradient descent. This is an example of a neural network which has an input layer, a hidden layer with 3 units, or neurons, an output layer with 1 unit, and between these 2 layers we have weights, or parameter values, and between these 2 layers we have another set of parameters, or weights, and those weights here are not just a vector anymore, they constitute a matrix. So we have those parameter values, so 3 values, and we have those parameter values that connects the input to this neuron, so 3 other values, and again we have those values that connects the input to this neuron, so 3 other values. So we have a matrix of parameter values or weights. And here we have a vector of parameter values, but we can consider this as a matrix also. So let's denote the first matrix of parameters by theta, big theta 1, or 1 here, and the second matrix of parameters as theta 2. And this is just our input data point x, so all this. And in this hidden layer we have also a vector, let's call it A2, and this 2 denotes the layer, here it's layer 2. So A21 is the first neuron in layer 2, A22 the second neuron in this layer, and A32 is the third neuron in layer 2. And this is our output. We can denote it, for example, by A3, because this corresponds to the third layer. But we shouldn't forget too that there is a bias unit here, x0 equals to 1. So we also have those weights in the first matrix of weights. So this is our input x, and x is a 4-dimensional vector, so it belongs to R4. And here we have the matrix of weights that connects this layer to this one, which has 3 neurons. So this matrix of weights is of dimension 3 by 4, because each unit is connected to the input via 4 weights. So this matrix theta 1 is a 3 by 4 matrix. And this matrix of weights is a 1 by 4 matrix, because here we also add this bias unit when we talk about this matrix. So the matrix theta 2 belongs to R1 by 4, so it can be considered as a vector. And this big theta here is the set of all parameters. So this theta contains both theta 1 and theta 2 in this example. And let's take again this example. So Aij is the activation of unit I in layer J. So if, for example, we take A32, this is what goes out of this neuron. So it's the value that you get from the activation of this neuron, neuron 3, in layer 2. And when we talk about theta j, big theta j, this is the matrix of parameters or weights that maps the layer j to layer j plus 1. So if we talk about theta 1, it maps layer 1 to layer 2, and theta 2 maps layer 2 to layer 3. Let's now see what is the value computed in each of those units. And let's not forget that we need to add this bias unit here. So in the first unit, we have 1 times this weight. So x0 times this weight. And here x0 is 1. So it's this bias unit. Plus x1 times this weight. Plus x2 times this weight. Plus x3 times this weight. And then we apply an activation function g on all this. So this part here is just the dot product between the input vector and those weights, or the first row in our matrix of weights. And we apply the activation function g on this dot product. So that's the value A12 that we get out of this unit. And something very important here when we talk about the activation function of a hidden unit, a unit which is in a hidden layer. For such unit, it is recommended to not use an activation function like, for example, the sigmoid. Instead, we use something called the ReLU, for example, the ReLU activation function. ReLU here stands for Rectified Linear Unit. And it's a very simple function, yet it's a nonlinear function. So g of s is equal to the maximum between 0 and s. So this ReLU function looks like this. So this is some value s, and this is g of s. So if s is negative, then this function gives 0. Otherwise, it gives you s. So you can use such a function in the hidden layer instead of the sigmoid function. And you can use the sigmoid function, for example, in the output layer, in the output units. For example, if you want to do binary classification, you want your final output to be something between 0 and 1. But we don't usually use it in the hidden layers or in the hidden units. And we will discuss more about this in the next video. But very briefly, this will give, if you use in the hidden units the sigmoid activation function, then this will lead to something called the vanishing gradient problem. And this will slow down the training of your neural networks. So preferably in the hidden units, use something like the ReLU activation function. Okay, let's move on. Now, what is computed in this neuron? Well, this is just the dot product of this input vector and those weights, or the second row in our matrix. So it corresponds to this part here. And then we apply an activation function to this dot product. So we get all this. So that's what we get out of this neuron. And what is computed in this unit is just the dot product of this input and those weights. So the third row in our matrix of weights. So we get this, and then we apply again an activation function, for example, the ReLU activation function on this. And if you look more closely, we can actually get all this in one step. So if we take our whole matrix of weights, θ1, so we're talking about this matrix, all those weights. And again, this is a 3 by 4 matrix. And if we multiply it by the input vector x, this is our data point, and this is a vector of dimension 4, so it has 4 rows, because we have here 3 features plus this one additional bias unit that we added. So it's a vector, but we can also consider it as a matrix of 4 by 1. So the dot product of this matrix of weights with x will give us a vector of 3 values. So this is a 3 by 1 vector or matrix. And we apply the activation function g on those values. So this corresponds exactly to the vector a2. So the values that you get out of this layer. Now let's see what is computed in this output unit. So this is simply the dot product of those values that we get out of this layer, of this hidden layer. And again, we don't forget to add this bias unit here. So we compute the dot product of this with those weights, and then we apply an activation function. And since here we are at the output unit, we can apply the sigmoid activation function. For example, if we want a binary classification, so we want, for example, our output to be between 0 and 1, then we can apply the sigmoid activation function here. And that's what we get out of this final layer. And this will be a scalar value in this case, in this example. And again, this part here is just the dot product of θ2, so this matrix of weights, and A2. But here I'm talking about A2 after adding this bias unit, this additional 1 here. So initially we had 3 values out of this hidden layer, but then we added this bias unit 1, so it's included here. And so this matrix is a 1 by 4 matrix. So 1 by 4. And this is a 4 by 1 matrix, or just a vector of 4 values. So it's a 4 by 1. And we apply our activation function here. For example, the sigmoid function, because this is an output unit. And this will be our predicted value. So it will be a 1 by 1, or just a scalar value. So to summarize, if we have a neural network like this one, for example, then if we take the matrix of weights θ1, this matrix connects layer 1 with layer 2. And in layer 1, we originally have 3 units because our input have 3 features, x1, x2, and x3. So we have 3 units. But we added 1 additional bias unit here. So in this first layer, we have 3 plus 1 units. And in the second layer, we have 3 units also. So θ1 will be a 3 by 4 matrix. So θ1 connects layer 1 with layer 2. So layer 2 has 3 units. So a 3 by 3 plus 1 matrix. And similarly, if we take the second matrix of weights, θ2, then this matrix will be a 1 by 3 plus 1 matrix. So a 1 by 4 matrix. So more generally, if you have a neural network with Sj units in layer J, and then you have some number of units in the next layer, then the matrix theta j will be of dimension this. So the number of units in the number of rows is the number of units in the next layer, and the number of columns is the number of units in the previous layer plus 1. And this plus 1 here comes from the fact that we need to add this bias unit each time. So when we talk about, for example, theta 1, this first matrix of weights, then we need to add a bias unit to the first layer. And when we talk about this second matrix of weights, theta 2, then we need to add a bias unit to layer 2. And that's where this one comes from. And by the way, when I'm talking here about Sj, this is just the number of units in layer J. So this has nothing to do with this S that I was referring to here. These are completely different. Another example to make things a little bit more clear. So in this example, our input data is a two-dimensional vector, right? So we have only two features, x1 and x2. And we decided that our neural network has 3 units in the hidden layer and 1 unit in the output layer. So the first matrix of weights, theta 1, will have 3 rows because we have 3 neurons in this layer. And it will have 2 plus 1 columns, so 3 columns. So it will be a 3 by 3 matrix. So this is our matrix, theta 1. The first row corresponds to those weights. The second row to those weights, going to the second unit. And the third row corresponds to those weights. Now, when you get a new data point x, described by a feature value for x1 and a feature value for x2, and you add one additional feature, x0 equals to 1. This is the bias unit here. And what you can do is to multiply theta 1, this matrix of weights, by x, by this input vector. And then apply the activation function g on each of those values that you get. So it will be this by this, the dot product of this by this. So you get some value here and you apply the activation function g, for example, the ReLU activation function. And then this by this, and you apply the activation function g. And then this by this, and you apply the activation function g. So what you get out of this layer is just g of theta 1x, right? And then what you need to do is to add a bias unit to this layer here. So this is equal to 1. So now after adding this bias unit, this vector will be a 4-dimensional vector. So it corresponds to all this. And we have our second matrix of weights, theta 2. This is a 1 by 3 plus 1 matrix. So it's a 1 by 4 matrix. It corresponds to those weights. And so we can multiply theta 2 with this A2, right? Like here. And then we apply an activation function G. For example, the sigmoid function here. And so that's our predicted output. So to summarize again, what is computed in this unit is just this dot product, and then we apply the activation function on the result. And then same thing here, we compute the dot product and apply the activation function. And same thing for this one, dot product, and then we apply the activation function. And as we said previously, the activation function that you can use for the units of this hidden layer can be, for example, the ReLU activation function. So preferably don't use something like the sigmoid function in those hidden units. And then for the output unit, you compute again the dot product of those weights with those values, and then apply an activation function. And the activation function g that you apply in this output unit can be, for example, the sigmoid function. For example, if you want your output to be between 0 and 1. But all those computations here can be simply summarized as just the dot product of θ1 with x. So you have your input vector x, and of course you add the bias term, the bias unit, x0 equals to 1. And you have your matrix of weights, θ1, which is in this example a 3 by 4 matrix. And so all those computations here are just θ1 by x. So you get a vector containing those values 1, 2, and 3. And then you apply an activation function g on those values. So you will get a vector a2. And that's what you get out of this layer. So to put this simply, the vector a2 is just g of θ1 x. And we compute this after adding the bias unit 1 to this vector x. And then we do a similar thing at the next layer. So we just add a bias unit to A2. So we add a 1 here. And so our matrix of weights, θ2, is a 1 by 4 matrix. So a 1 by 3 plus 1, a 1 by 4 matrix. And so the output of this layer is just g of θ2 by A2. So this matrix of weights by those values that we get out of this layer. And you can repeat the same thing again and again if you have more layers. We said previously that this is our matrix of weights, θ1. And we said that this is a 3 by 4 matrix. So 3 by 4. And our input vector x has 3 values plus 1 bias unit. So it has 4 values. So x is a vector of 4 values, or a 4 by 1 matrix. And we said that we need to apply an activation function g on this. And so this will be the output that we get out of this layer. So this is equal to A2. So this is a vector of 3 values. So it will be a 3 by 1 vector. And then we said that we do a similar thing in the next layer. So we add a bias unit to this A2, right? And then we compute θ2 multiplied by A2, and we apply another activation function here. And we get our output. But what if now we don't have just one data point x, but instead we have n data points? So we basically have a whole data set, or an input matrix, big X, which has n data points and d features. Or let's say d plus 1 features if we count the bias unit, or the additional feature x0 equals to 1. In this example, d is equal to 3 features plus 1 corresponding to the bias unit. So let's say that we have an n by 4 matrix. And so this matrix corresponds to a data set of n examples instead of just one example. So what we can do in this case is to use X transpose here. So this will be an n, it will be a 4 by n matrix. It's just the transpose of this one. And so what we will get will be a 3 by n matrix. So instead of just getting one vector with 3 values, we will get n of them, right? N vectors. 1 for each data point. And then we can add a bias unit here. So we will have 4 values instead of 3. So A2 becomes a 4 by n matrix after adding the bias unit for each data point, or for each of those n vectors. So now we can take the matrix of weights θ2, which is a 1/4 matrix, and multiply it with A2, which is a 4/n matrix. And we apply another activation function, and that's what we will get out of this output layer. So the whole thing here will be a 1/n matrix. So we will basically have n output values. So one output for each input data point in our data set. One interesting observation is that if we look at only this part of the network, then this corresponds to simply a logistic regression model, if we use the sigmoid activation function here. But instead of using the original input features x1, x2, and x3, this logistic regression model is using A1, A2, and A3, those values that are out of this layer. So this part of the network is just a logistic regression model, which is using those new features that we get here. And those features that we get at this layer are computed based on the original features. So basically, the neural network is transforming the input data, or those features, into new features. So it transforms the data into another data, and then applies a logistic regression on those on the data described by those new features. So we basically say that a neural network learns its own features. So in this example, it learns 3 new features based on the 3 original features, and then just applies a logistic regression model on the data described by those new features. But of course, in this lecture, we didn't yet talk about learning or how to train the neural network, but we will see this in the next lectures. We will see how to train the neural networks. And this means how to find the values or the optimal values for those weights. But what I want you to observe here is that by training a neural network, you are actually training it to transform the original features into some new set of features. And then based on those new features, it does classification or regression or whatever you want. And so far, we have seen examples of neural networks with just one hidden layer, but nothing prevents you from adding more layers. So in this example, we have a neural network with 2 hidden layers. So layer 1 is just the input layer, and then we have layer 2 and layer 3, and then the output layer. So if you train such a neural network using some training data set, and you optimize some cost function in order to find the best weights or the best values for those parameters, then what you are basically doing is learning to transform the input data described by those original features into a new set of features. And then based on those new features, you are learning 2 other features that are based on the previous ones. And then based on those 2 new features, you are, for example, applying a sigmoid activation function here in order to predict the output, for example, for binary classification. So when you have a deep neural network with several layers, it will learn some features in the initial layers, and then based on those features, it will learn higher level features and so on. And then it uses the final features that it learns to make predictions. We will discuss more about this when we talk about how to train a neural network. Another thing that we didn't mention is that you can have a neural network with multiple units in the output layer. And this is typically used when you want to do multi-class classification. So when you have more than 2 classes. If you want to do regression, for example, you want just to predict one value, then you can have 1 unit in the output layer. And if, for example, you want to do binary classification, so you have only 2 classes, 0 or 1, then you can also have 1 unit in the output layer. and you apply a sigmoid function on this unit so that the predicted value will be between 0 and 1. And then if it's closer to 0, you say that the predicted class is 0. And if it is closer to 1, you say that the predicted class is 1. But when you have multiple classes, like for example 4 classes, then you can use 4 units in the output layer. And the way to do that is to encode the labels in your training dataset as a one-hot vector. So each label will correspond to a one-hot vector. For example, if we have those 4 classes, pedestrian, car, motorcycle, and truck, then an image labeled with this label, pedestrian, this label will be encoded as this one-hot vector. So it's a vector which contains four values because we have 4 classes. And then there is only one value which is 1 and the others are 0. So 1 at the first position here indicates that this is a pedestrian. And 1 at the second position indicates that this label corresponds to a car. And here it corresponds to a motorcycle, and here to a truck. So each label is a vector of 4 values because we have 4 classes and we have 4 output units here. And so when you get an input data point x, its corresponding predicted output will be a vector of 4 values. For example, here you get 0, here let's say 0.7, here for example 0.1, and here 0.2. So you will for example say that this input probably corresponds to a car. And you can check the difference between the predicted output and the true output or the true label. For example, later when you want to train the neural network. We will talk more about this in the next lecture. So again, here in this example, each output will be encoded as a one-hot vector, like those. And you want your output to be a vector of 4 values in this case, because we have 4 classes. And you want each value to be between 0 and 1. And the way to do this is to use at this output layer an activation function called the softmax function. And we will talk more about this later in the lecture. So to summarize, you can have a neural network like this one with one output unit. And you want this usually if you want to do regression or binary classification. Because in regression, the output is just one value. It's a continuous value, so it belongs to R. And your predicted value is also in R. So you want the neural network to be able to output any value. And in binary classification, the true output is either 0 or 1 because you have only 2 classes. So you want your output to be in the interval 0 to 1. So for a given data point x, if the predicted value is closer to 0, then you say that the predicted class is 0. And if it is closer to 1, you say that the predicted class is 1. And to do regression, you usually apply a linear activation function in this output unit. So linear activation function is just this. So g of s is equal to s. So you compute the dot product of those weights and those values, and then the activation function is just this dot product, right? Because you want to be able to output any value in R. And for binary classification, the activation function that you apply in this output unit is usually the sigmoid activation function. And as you know from previous lectures, this will give you values between 0 and 1. And if you want to do multi-class classification, then you can have an output layer with multiple units. So if you have C classes, then you will have C units. And in this case, you need to encode the labels in your training dataset as one-hot vectors in order to train such a neural network. So in previous lectures, we had an input matrix X, right? which has n rows corresponding to n data points and d columns corresponding to d features. And we have a vector y of all the outputs. For example, in the case of regression, it was n outputs. So one output for each data point. And in the case of classification, this was a vector of n rows. And each value here is the label corresponding to one data point. So for example, we have class 0, the second data point also belongs to class 0, then we have the third data point belongs to class 2, and so on, right? Now, instead of this, each label yi, so the label corresponding to the ith data point, will be actually encoded as one hot vector. So it will be, in this case, for example, 1, 0, 0, which means the first label 0. And you can transpose it if you want so that you get a row here. So basically your labels corresponding to the training data set will be something like this. So for example, the first data point has label 0, so the one hot vector will be 1, 0, 0. The second data point has also label 0, so it will be encoded in this way too. And the third data point has label, for example, 2, so it will be encoded 0, 0, 1. And the fourth data point, for example, has label 1, so it belongs to class 1, so it will be encoded as 0, 1, 0, and so on. So that's how your input and output will look like if you want to train a neural network which looks like this. And for this multi-class classification problem, you want your output to be a vector of C values where each value is between 0 and 1. So for example, for a given input, you get this output. So for example, this input has 0 probability to be a pedestrian, it has 0.7 probability to be a car, 0.1 probability to be a motorcycle, and 0.2 probability to be a truck. So we have 4 classes. And we want those values to sum to 1. So to do this, we use a softmax activation function at this output layer. So when you compute the dot product of this matrix of weights with those values that you get out of this layer, then you get a vector of values, let's say S1, S2, S3, and S4. And then you apply the softmax activation to this. So let's call it G. And this is the vector of outputs that we got here. So for example, this is how you would compute G of S2. And this denominator here is used for normalization so that the sum of those is 1. And for the units in those hidden layers, people usually use something like the ReLU activation function. And it is defined as G of S equals to the maximum between 0 and S. And there are some other alternatives like the leaky ReLU, for example, but we will discuss more about those later in the course. As you may guess, a neural network is a quite complex model because it depends on a lot of parameters. So depending on the number of layers that you have and the number of units in each layer, then you will have more or less parameters. But in general, a neural network can solve very complex problems. For example, in classification, it can approximate very complex decision boundaries. And we say that a neural network is a universal approximation function. It can actually approximate any function, no matter how complex it is. So in theory, a neural network with at least one hidden layer can approximate perfectly any function. So this means that there exists a set of parameters or weights that can produce the output from the input. Now the problem is to find those weights. And we will talk more about this in the next lecture, where we will see how to train a neural network. And things like the number of layers and the number of neurons in each layer and so on, these are hyperparameters. So in practice, people try various neural networks architectures, meaning different number of layers and number of neurons, and then they see which one leads to better results.